In this section, we are going to be studying Bayes' theorem. And Bayes' theorem is one of the most important theorems in all of probability. So let's start with a question. It says, a regional producer of soft drinks fills and caps cola bottles on one of three machines in its plant in Decatur, Georgia. 20% of the total output goes through machine 1, which has a 0.1% defective rate. That is, only 1 out of every 1,000 bottles that is processed on this machine is improperly filled or capped. Machine 2 handles 30% of the output with a 0.6% defective rate, and machine 3 processes the rest of the bottles with a 0.4% defective rate. I'm going to want to finish the tree diagram that is started for us. So I already started by adding in some of the notations, and now let's go through and put in the actual number values. So they set up the probability of going through machine 1 as 20% because 20% of the total output goes through machine 1. So if you were to randomly pick a bottle, 20% of them, there's a 20% probability that it went through machine 1. So let's see. Machine 2 handles 30%, so we want to put that on that line. And machine 3 handles the rest, so 20 plus 30 is 50% accounted for already. So machine 3 must handle the other 50%. Okay, and then they've got the very top, the next from M1 going to D for defective, they've got that labeled. The probability of being defective, given that it comes from machine 1, is 0.011. That's that 0.1% defective rate. So we're going to use complements to figure out the rest of these. So let's see, if 0.011 are defective, then 0.999 are not defective coming through there. Now, the probability of being defective knowing that it came from machine 2, well, machine 2 had a 0.6% defective rate, so that would be 0.006, leaving 0.994 for not being defective given that it came from machine 2. We also know that given that it came through machine 3, that is a 0.4% defective rate, so 0.004 leading to defective, and 0.996 leading to not defective. Now, if we want to find all of the intersections, all of the ands, remember how we can just follow each branch out multiplying. So the probability of coming from machine 1 and being defective, they calculated already for us by doing 0.2 times 0.001, and they got 0.0002. To fill the rest of these in, and I'm going to go through them sort of quickly, but you can calculate these on your own off to the side. The next one will be 0.2 times 0.999, and that gives us 0.1998. The next one is 0.3 times 0.006, which gives 0.0018. The next is 0.3 times 0.994, which is 0.2982. And then we have 0.5 times 0.004, which is 0.002. And 0.5 times 0.996, which is 0.498. So we have every possible part of this tree diagram labeled. So now we look and it says, the event bottle is defective can be broken down into 3 mutually exclusive cases corresponding to the 3 machines used to fill and cap the bottles. Each of these cases is represented by a different branch in the diagram that ends in defective. So if we want to find the probability that a bottle is defective, we can just add all of the intersections together. So we can follow all of the branches that end in D and add all of these go back on that, wrong one. Add all of the probabilities, the intersections that came from the defective branches together to find the probability that any bottle is defective. So in this case, that would be 0.0002 plus 0.0018 plus 0.002. And if we add all of those together, we get 0.004 or 0.4%. So regardless of the machines, the probability that any one bottle is defective is 0.4%. Let's do another example with the tree diagrams. Suppose a box contains 2 defective Christmas tree lights that have been inadvertently mixed with 8 non-defective lights. If the lights are selected one at a time without replacement and tested until both defective lights are found, what's the probability that both defective lights will be found on or before the third trial? Use a tree diagram. So I know that I hate messing with Christmas lights. This is a very applicable situation for me. But let's see, our first branches, when we start here, we're either going to choose a defective or a good bulb. So that's why I'm going to label my branches D for defective and G for good. Now, it says there are 2 defective lights mixed in with 8 non-defective. So there's a 2 out of 10 probability that I'm going to choose a defective one, and an 8 out of 10 probability that I'm going to choose a good one. And in a situation like this, I would recommend not reducing those so that you can use those as you move on. So leave them in their unreduced form. It'll be helpful later. Now, regardless of whether you found a good or a defective one on your first choice, you're going to draw again out of this box. And again, you could either pick a defective or a good bulb. But look how the probabilities change. If I've already picked out a defective, now there's only 9 bulbs left to choose from. So all of these next denominators are 9s. And depending on what I've already picked is going to change the numerators. So what's the probability, if I've already picked a defective one out, what's the probability of picking another defective out? Well, now there's only 1 defective left in the box out of 9 that are in there. And there are 8 good ones left out of the 9 in there. So that helps me fill out those top 2. If I picked out a good one first, then there are still 2 out of the 9 that are defective, and only 7 out of the 9 that are good. Okay, so one more draw for our third draw. Let's see, if I've already chosen, well here, let's see, all of the denominators now have to be 8s because that's how many, I'm starting to get a little crowded in here, but that's how many bulbs are left. If I've already picked out or chosen both defectives, then there are no defective bulbs left. There's no way to pick a third defective bulb. If I've picked 2 defectives already, the probability of picking a good one next is 8 out of 8. They're all good that are left in there in that case. Now, if I've picked a defective and then a good, there's 1 more defective left I could choose. Sorry, I forgot to label these. These should be D's and G's all the way down. And if I've picked 1 of each, then that means there are also 7 out of 8 good ones left. Similarly, if I picked a good and then a defective, there would be 1 out of 8 defectives left and 7 out of 8 good left. And if I picked 2 goods in a row, then there would be 2 out of 8 defectives left and 6 out of 8 good left. So now let's see. The probability, they want to know the probability that we have found both defective lights. So let's see, in which ones of these branches have we found the good, or have we found both defectives? That would be the top branch, we found them in 2. And then we have D, D, G, so we found both defectives there. D, G, D found both defectives. But D, G, G did not, so I'm not going to keep that one. Good, defective, defective found both. Good, defective, good didn't. Good, good, defective didn't, and good, good, good didn't. So what I see is I see 4 of these branches leads me to finding both defective lights after 3 draws. So I need to calculate up the ands for these 3 branches and add them all together. So what's the probability of choosing a defective, defective, good? Well, that's 2/10 times 1/9 times 0/8. So I end up multiplying by 0, so that's just a 0. What's the probability of picking defective? Oh, sorry, that was defective, defective, defective. So yeah, that one didn't make any sense. Never mind. We're not choosing that one. That one doesn't make any sense. That's not a case that would actually happen. We'll just get rid of that one. So there was really only 3 branches that make any sense here. Finding the probability of choosing out a defective, and then a good, I would multiply 2/10 times 1/9 times 8/8. If I multiply that all out, you should get 1/45. Similarly, what's the probability of choosing defective, good, defective? That's 2/10 times 8/9 times 1/8, which is also 1/45 if you multiply that all out. And what's the probability of choosing good and then defective, defective? That's 8/10 times 2/9 times 1/8, and I'm just following those probabilities out on that branch. And that is also a 1/45. So the probability of choosing a defective or both defectives, so I'll call that 2 Ds, by the 3rd draw is whatever we get when we add all of those probabilities together, because those are all the ones that apply to this particular situation, and they're all mutually exclusive. There's no way to do any 2 of those situations at the same time. So we would add 1/45 plus 1/45 plus 1/45, and that would give us 3/45, or 1/15, which divides out to about a 6.7% probability of finding both of those defective lights, at least by your 3rd draw.